Welcome to Mr. Math Academy. Grow your math brain.
Hello friends, welcome back to Mr. Math Academy. So today in this video we derive the equation of a member which is subjected to a pure torque here. Okay, this derivation is important for the examination point of view in all the universities. Okay, now let us consider how we can able to derive this. Okay, let us consider a given shaft is there which is of length L, now which is having a radius R, it is subjected to a pure torsion, that is a twisting moment T. Now this is fixed at one end and the free at the other end. Now in such cases what will be the equation, what will be the twisting moment, what will be the torsion equation, we just find. Now let us consider this point AB, that is it will be a layer here which is we have mentioned in the outer surface. Now what happens when we just apply the twisting moment T here, so this point, that is the location of this B, will be shifted to the B dash here. Okay. Now when it comes, because when it is subject to a twisting moment T, the point B will be shifted to the B dash here, which makes an angle phi here. So which makes an angle phi, but on the other side if you just see from this side again, we can just see there will be one more angle theta is there. So that theta is nothing but our angle of twist, that is how much angle of angle that you are twisting the shaft here. Okay, now here in this case the phi indicates it's a shear strain. Now we just derive how we can proceed here. Now let us consider, now this AB is our initially the original reference line here. When it is subjected to a twisting moment T, it is shifted to the AB dash here. Now from this, if I just take the AB and B dash, how we can see this kind of figure, you can see this is our phi, this is a point A, this is B and B dash here. Okay. Now from this figure, because how I am taking from this particular sketch, okay, from this side if I just see, we can get this kind of form here, that is the A, B and B dash. You can just see this is our phi here. Now from this figure, if suppose if I consider this is a figure A, now I will take here from figure A. So what is the tan phi? I will just calculate what will be the tan phi here. So tan phi becomes, it's a opposite, that is a BB dash by AB. So that is tan phi becomes, it's a opposite BB dash by AB here. Now we know that by the geometry, so for a small angle the tan phi becomes phi. I will take for small angle tan phi, I can take this as phi. Therefore this phi becomes B dash by, so AB is nothing but it's our length of the shaft here, what we are taking here, that is a L here. Now this I can write it as BB dash is equal to L into phi. Okay, I will just take this as some equation 1. Now there is one more figure, you can just see from this side if I see here, so we can have a arc here, that is a B dash, which makes an angle theta here, that is the angle of twist, whose radius is R from the center. Okay, if I want to find out the B dash is nothing but, if I take this is a figure B, so from this, from figure B, so B dash is nothing but our length of arc, which is given by the radius into angle subtended by that particular arc, that is the theta here. Therefore I can take this BB dash as R into theta. So if I take this as equation 2, now you just equate equation 1 2 because of the BB dash. So equate equation 1 and 2, which gives L into phi is equal to R into theta. So again this phi becomes R theta by L. So this I just take a equation 3, where phi is a shear strain in the section. Okay. Now the next thing is, so we know that the Hooke's law, by the Hooke's law what we are getting, the modulus of unity G is equal to, it's a ratio of a shear stress to the shear strain, that gives the ratio of a shear stress by shear strain. Now from this, if I take phi is equal to tau by G, I will write here from Hooke's law, we know that So G is equal to, directly I'll write that phi is equal to, it's a tau by G. So this is our equation 4. This is the equation from the Hooke's law here. Now we just equate the equation 3 and 4 because of the same of the phi here. I just equate equation 3 and 4. So which gives r theta by L is equal to tau by G. From this, tau by r is equal to, you just cross multiply here, tau by r is equal to, I can take like this, G theta by L. So this I take as equation 5. Why I have taken means because this is our first part of the given derivation, and that is a derivation here. So that is tau by r is equal to G theta by L, where tau is a maximum shear stress in the that is a member which is having a radius of r. G is a modulus of rigidity. Theta is nothing but an angle of twist, and the length is nothing but this is our length of the given shaft here. Now we can just see here, for a given shaft the modulus of rigidity is a constant, T is angle of twist is also a constant, and the length of the given shaft is also a constant. So means what, this tau by r is a constant for a given shaft. Now we just move on to the next step here. So if I consider a small differential element, if I take the section of this on the right hand side part, I am considering a small differential element of area dA, so which is at a distance of small r. Okay. Now it is subjected to a force of dF here. Now I just try to find out what will be the torsion, that is what will be the torque in this particular differential element. So we know that if I take dt is equal to, that is a torsion, that is a torque in this particular differential element as dF into r. So like torque is equal to twisting moment is equal to force into perpendicular distance, that is a force into radius. In that form I have taken this dt is equal to dF into r. This is our force for a small differential element. Now in place of dF, how we can take, if suppose for example we know that shear stress tau is equal to, it's a force by area for a differential element. So I have mentioned tau dash is nothing but a shear stress for a differential element. If I take only a tau here, this is a shear stress for the entire section here. Now tau dash is equal to force by area, because like general stress equation, stress is equal to load by area form. Okay, from this equation if you just cross multiply here, we are getting dF is equal to tau dash into A. Therefore dt is equal to tau dash into dA into r. Okay. Now from this what I can write here, if you just take this particular equation, that is right here, okay, tau is equal to G theta by L into r. I am just considering the equation 5 here. If suppose if I put r is equal to 0, that is at the center, we can just see the shear stress will be 0. Again when the radius increases, the shear stress will also be increases. Means what, the shear stress will be varies linearly with respect to the radius of a shaft here. Therefore this tau dash I can write G theta by L into r. Means what, this is the tau dash is the shear stress when the radius is r, by using the same equation. Okay. Now what happens if I take the equation 5 here, that is a tau by r is equal to G theta by L. Now we can just see G is a constant for a given shaft, theta is also a constant, and L is also a constant, that is a constant. Similarly tau dash by r is also a constant. Okay. Now by using this constant, that is a condition, I can write it as tau dash by r is equal to, tau by r is equal to constant. By using this concept, I can take this tau dash by r is equal to, tau by r is equal to constant here. Okay. Now by this condition, tau dash I can write it as tau by r into r. So I'll just substitute this tau dash in this equation here. So what I can get, so therefore dt is equal to, that is the tau by r into r. This is our tau dash. Now here there will be a dA is there, and this is our r. Okay, now this is the torque for a small differential element. If I want to find out the torque for the entire section, we just have to integrate this equation for a given range here. Now I will consider on integrating the equation, this equation I will just take this as equation sum 6. Integrating the equation 6 here. So the left hand side directly I just mentioned, it's a t here. The right hand side part I will just integrate from 0 to r. Since the tau by r is a constant, this tau by r is a constant, I will take outside the integral form. Now the remaining terms are r into r square, and dA will be left here. Okay, now this is the form what we are left here. Now we can just see this integral from 0 to r square dA is nothing but our polar moment of inertia for a given member. So I will just take, this is our tau by r, that is the t is equal to tau by r into j. So where j is equal to, that is the integral 0 to r, it is a r square into dA, that is our polar moment of inertia. Okay, now from this equation I can take this t by j is equal to tau by r. Now I will just take this some equation 7. Okay, now this is our second part of the derivation. The very first part is our what? Tau by t by j is tau by r is equal to g theta by l. We are getting at the equation some 4 or 5. Therefore, from equations 4 and this one 7, we can write this as t by j is equal to tau by r is equal to g theta by l. So this is our torsion equation, that is the torsion equation for a given particular shaft, where t is a twisting moment, j is the polar moment of inertia, and tau is the maximum shear stress, and this is the radius of the shaft, modulus of it is g, theta is angle of twist, and the length is l is a given length of the particular shaft. I hope you are getting this equation, simple equation. So this is a very important derivation for the any examination point of view. Okay, if you like this video, please comment, share with your friends, and subscribe to our channel.